Thank you, Siegfried, for kind introduction. It's my pleasure to me. I have been to many fracture conferences, ECF and ICF, but I never got an award. In all of those conferences, I'm sure I'm the participant from the farthest point in the world. So I'm from Melbourne, which is 15,000 kilometers, but there's no award for participant from the furthest country. Anyway, so first of all, thank you so much for inviting me on the podium to talk about our research, which we are doing in our Center for Additive Manufacturing in Melbourne, Australia. I first like to acknowledge my co-presenters. So this work is largely based on the work done by Laboni Afroz for her PhD and with professors Mark Easton and Qian. Now, my title says, Damage Tolerance and Structural Integrity of Additive Manufacturing Components, Challenges and Opportunities. So I'll present in that way. I'll open up the challenges. And the way I will do it, I'll show some of our experimental work and the data we have found. And we'll try to explain why we found what we saw. And then I will open up challenges to the particularly next generation researchers, our early career and young researchers which are in the room, to solve some of them. And let's see how it goes. And if they can solve it, there's a prize for that. Okay, so just a quick introduction of our group. We are a group at RMIT Center for Additive Manufacturing, and these are the numbers: about 21 academic professors, full-time researchers, about more than 40 PhD students. It's a quick introduction to what we do, where we are, so that you have an idea, and if you need to talk to me later on, we can obviously love to talk to you. So these are some of our members, and this is our building in Melbourne outside, and these are internal lab facilities. So we are unique in Australia. We cover both all sorts of materials for additive manufacturing, including metal, polymer, and that is coupled with, in the same floor, our all additive manufacturing systems are within the what we call additive manufacturing printing. We have 3D printing, we have CNC, and other facilities together, and mechanical testing where we can do complete research. Moving forward, this is thanks to my group. This is my particular research group. We work on additive manufacturing, but or many other problems in mechanics. So my thanks to these students who have helped our group to grow and in the field of particular additive manufacturing, but also fracture and fatigue and computational modeling. So these are my kind of the research areas I have worked in the past 2 decades since I did my PhD. That mainly covers fundamentally coupled solver algorithm, mesh-free finite element method development, and coupling that with damage mechanics and constitutive mechanics. And in terms of applications, we have worked in damage tolerance optimization, we have worked in dynamic fracture and impact response, and we have been working, and of course, the new area of fascinating research of our group is architectural materials and metamaterials, and all in the context of fracture fatigue behavior and how we can fabricate it in the context of additive manufacturing. In terms of application, we work a lot with aerospace industries. So multifunctional lightweight structures is one of our key applications of research, coupling with, say, morphing structures, morphing wings, and it's basically focused towards aeronautical and space. With that background, let's talk about the focus topic, which we can only cover in one plenary. That is, we are looking at aluminum alloy, particularly ALSIMG, which is a common additively manufactured material because our focus is customized, just-in-time manufacturable aerospace components. That's why we are focusing on aluminum alloy. There has been a lot of attention on AM titanium alloy because of its use in high-end applications, but aluminum alloy has received less attention, particularly because of their not so good properties. But we have to make it good, and we have to use in aerospace. There is no escape from that. And that's why I'm focusing on this material for today's presentation. And so the challenges in fatigue, and particularly AM fatigues, are there are a lot of complex net shape design, just-in-time production, and many other fields where fatigue is very important. Now, what you see here is growing application in aerospace and automotive industry. So we can't deny the role of additive manufacturing, and then the components manufactured needs to be certified for structural integrity and fatigue life assessment. Now, let's present the whole summary in one slide, what the problem is. So we are interested in cyclic properties, and we are all know in additive manufacturing, we can control one of these parameters: powder properties, process parameters, heat treatment, machining, post-processing parameters. Now, normally, we would like to link our process properties with the cyclic properties. But additive manufacturing brings certain complications and challenges, which are in this layer. We are looking at how these parameters contribute to defects, microstructures, surface roughness, residual stress, and anisotropy. And this is what I'm going to unravel in today's presentation. Particularly look at these arrows. Powder properties affect defects on microstructure, heat treatment would affect defect microstructure, surface roughness, residual stress, anisotropy, all of it. And same does, machining does affect surface roughness. Process parameter affects defects, microstructure, surface roughness. Now, when I say affects, some of the cases, same process parameter will produce defect, which will affect in a negative way, which will reduce the fatigue life. But same process parameter can produce elongated microstructure or coarsening of grains, which can actually improve fatigue life. So look at that point. The same process parameter can produce two effects. One is improving, one is decreasing. So they are synergistically opposite. And that brings the challenges optimizing these parameters to maximize our fatigue performance. So that's what we need to focus when we deal with additive manufactured components, particularly aluminum alloy in this case. Let's look at a few systems which we are focusing on. I won't go in detail because I believe most of you in this room are familiar with that. Now, our focus, the process I'm focusing today is powder bed systems. And we have powder bed, powder fed, and wear fed systems. We are looking at powder bed system for our lab, and we use that a lot to make additive manufactured components, which is basically you have a powder bed, you have a laser canner, you have a chamber, and you put a laser beam to locally melt the powders to form the parts, and you lift or you raise or lower the bed plate to form the part continuously. So these are different types of powder bed. So that's the powder bed system, and there's a powder feed where there's a hoppers through which the powders are fed, and there is additive manufactured deposit, and the power supply will actually melt the laser power will melt the powder and solidify it in situ as it progresses. So let's go forward, and I would skip some of the initial slides, the background, because I want to get to the right points of what our results are, at what mechanisms we do understand. So why we are focusing on aluminum alloy? As I said, they have great ductility, high strength to weight ratio, good corrosion resistance, weldability, low thermal expansion, and so forth. So this is a material of choice, particularly for aerospace. We can do complete melt and solidification of powder. We can produce customized material and good mechanical properties. So if you have an aircraft, a part of a landing gear is broken, we won't use aluminum for that, of course. But any other component is broken, a bracket is broken, you can send a CAD file immediately with an automated way, and it can be produced within a couple of hours. That's not possible with the traditional part storage system, what we use, and that's the attractiveness. Now, let's look at the first research challenge, the process parameters, where we can control powder quality, laser power, scan strategy, and build orientation, and layer thickness. As you can see, the same component can be produced with a 90-degree build 90-degree scan strategy, or 67-degree scanning, or 180, which is completely opposite, or 79-degree, or any angle, whatever. So the scan strategy coupled with the build orientation, whether you build along X, Y, or Z axis, will the first point which will change and affect your part and can produce a controlled or uncontrolled anisotropy in some cases that we need to deal with. So the second point, obviously, is the defects that are produced and sometimes inherent to additive manufacturing. And these are gas ports, lack of fusion ports, and surface roughness. The gas ports normally happen due to entrained gas porosity. Sometimes we can get lower keyhole ports. If your scan speed is too slow, you get a porosity, but often you can get at a faster scan speed, the hierarchical pore. So there is no good solution of the scan speed. You have to optimize depending on what type of pores you want, but you can't escape from pores completely. So that's what the key point is to note. So N10 gas will either produce lower keyhole, or if you can produce slow or higher keyhole pore. And you can see some of the examples here. Now, lack of fusion happens due to poor bonding. Because of the unmelted metal powders, which stays due to poor bonding, you can create what we call lack of fusion, and you can end up with these unmelted metal particles or agglomerats. We call them satellites. Now, that's the type of defect we need to deal with when we are dealing with AM components. Finally, the surface roughness, which is well known to us. Surface roughness affects fatigue performance. The way AM process affects surface roughness, we need to understand and probably produce surfaces which are free from crack initiators or roughness defects. So these are kind of a summary of what I kind of described the challenges. Gas pores are spherical in shape. Normally, we are looking at 10 micron. It is normally due to the moisture and entrapped hydrogen sometimes. 50% reduction we can achieve. One solution to the challenge is we can hit the base plate, which we should adopt. Secondly, lack of fusion pore is related to the scan speed. So if we can optimize the scan speed or laser power input, layer thickness, we can control the lack of fusion pore. As I said, higher scan speed will cause incomplete filling, whereas lower laser input can cause unmelted powder particles. So a combination of laser input and scan speed in an optimized way can reduce the lack of fusion defect. So these are the two parameters we need to focus when we are using additive manufacturing. Okay, the next is inert gas flow is another factor. If you don't have sufficient inert gas flow, then it can cause also LOF defects in the additive manufacturing components. And surface defects are features also affected by the build rate. Okay, now what is important from this slide is I would like to highlight the role of microstructures. And this is an example of 3 different metals, which I'll show. First thing we did with Ti6L4B, the titanium alloys. And what we can see, the typical wrought metal has got globular alpha with alpha plus beta matrix, whereas the LPBF, we can see martensitic and columnar prior beta gain boundaries. So that's a typical of, from literature we found, this type of microstructures are produced. You can achieve within AM of titanium alloys a laminar microstructure by post-heat treatment or preheating the base plate. A preheating base plate acts as a heat treatment, in situ heat treatment. Fine microstructure, particularly with as-built AL alloy, happens due to rapid cooling, which leads to high hardness, yield, and tensile properties. Then, if we look at the steel, which is what is a key focus for AM for different applications, normally we find a finer and elongated microstructures. Melt pool boundaries you can easily be found easily distinguishable. But if we use suitable heat treatment, we can make the laser tracks disappear. So coarsening of microstructure happens, which is farther from the build plate. So what we get here for steel in the literature, a gradient microstructure, a fine scale microstructure close to the build plate, and it becomes coarse as we move far away from it. Now, with these features, if we look at now how it affects fatigue properties, here is a chart which shows you maximum axial stress versus different types of processing condition as built, machined and stress relieved, machined as platform hardened, platform heating, and machined as peak hardening. And you could see in general, if you look at this diagram from these papers, in general, we find with the post-processing treatment, machining and base plate heating, we can improve 50% fatigue life, roughly. Now, if we combine different post-processing treatments, such as peak hardening and machining, we can improve fatigue properties significantly. As you can see here, from all of them, we found if you machine the fatigue life, the maximum axial stress goes up for all of these cases. And if you look this one, where our machine plus we have done peak hardening, you can get significantly high maximum axial strength. Now, this again summarizes what we found so far in the literature. And we are going to explore what happens for these effects when we look at our target alloy, in this case, ALSI Mg, in the context of additive manufacturing. So that's coming up the next following. What we found, the controlling factors are surface roughness, porosity, microstructure, and isotropy residual stress. So these are what we call the key parameters of focus, the major parameters where the fatigue life is highly sensitive to. How it affects? Surface roughness of QSD failure initiates at surface or subsurface. If we do machining, we can improve fatigue life, but one problem is higher scatter, which we talk about in the rest of the presentation. Porosity control, the crack initiation size, but it has a magical effect, as you will see later. Out of the three things, a given pore's location, size, and pore volume, the location has a greater effect than pore size and the pore volume. We tend to think a larger pore will significantly reduce fatigue life. It's not always true. A pore could be spherical or pore could be different shapes, and that will control the fatigue life. Now let's look at what happens with the build direction. First is the printing direction is an issue. In general, what we found, if the printing direction is in parallel or 0 degree with the crack growth direction, we get a lower life and lower fatigue threshold, as you see for all of those cases. But you can use heat treatment or other post-processing treatment to improve the fatigue life. So that's challenge and how we overcome it, and we can control the printer. Secondly, our main objective is, why we summarize here, we were looking at printing direction we talked about, but the key parameters are stress loading, surface subsurface defect, post-processing, and build orientation. And our whole goal is how the size, effect of size, and types of AM-induced defects, such as surface and subsurface defects, and fatigue condition, stress ratio, affects the fatigue strength and crack growth threshold properties. This is an important factor. We want to understand, because post-processing is often used, having known our objective one, if we now apply post-processing techniques, so then the next step was how we look into the effect of post-processing condition on the fatigue life and how we can improve them. And the green was the digital world, which we have worked a lot. We have developed multi-scale finite element model to understand damage accumulation due to fatigue and how it affects fatigue life. And finally, we looked into what we call quick fatigue prediction for AM alloys using the so-called similitude laws, which are popular fatigue laws in literature. You can relate different alloy properties. Based on one data, you can develop another curve. So these are the methodologies, which we don't want to go through, with this high cycle fatigue test, fracture crack growth test, fracture toughness test, and those cycle fatigue. And these are the material properties and the chemical composition which we used. So basically, we looked at 2D and 3D defects with CT and SEM, looked at the surface roughness with a profilometer, used different build directions, series of build directions, 0, 90, 45, two different load ratio, completely reverse, and positive loading, and we looked at as built, machined, and heat treated. And we did a detailed SEM scanning of the material. This is the different equipment we used. And let's talk about what we see in the build orientation. How much time left? 10 minutes. Okay. So the first challenge I mentioned, build orientation, and what we saw there. Look at this plot. This is stress amplitude versus cycles to failure, fatigue life. If we see this is R -1, completely reverse loading. If we look at with stress amplitude, of course, fatigue life, if the stress amplitude increases, the fatigue life decreases, as we see as a high amplitude. Now, at a high stress amplitude, what we found, there is less scatter and there is little effect on build orientation, which is kind of contradictory when we found it. At a low level of stress amplitude, we again don't find well correlation, but what we find a larger scatter of data for these three build orientations we tested, 0, 45, and 90. So, and we have used a porosity fraction, not too big, very small, 0.1 to 0.5. Average roughness was less than 700 nanometer, and we machined and polished. So we wanted to suppress the effect of porosity and roughness. We want to highlight what is going on with the build direction. This is the results we found. In general, yes, for high amplitude, you can clearly see a 90-degree, 0-degree, and 45-degree build. For example, 150, you can get a higher fatigue life with a 90-degree build as compared to a 0-degree build. 45-degree is kind of same as 90-degree. At a lower stress amplitude, you can see a 0-degree build gives you higher fatigue life, in this case 100, and then again with a 90-degree and 45-degree, it lowers the life. Now the question is, we can't find any correlation with the build direction, and we were wondering what's going on with this alloy, because we knew people have complained that ALSI 10mg is not a fatigue-friendly material, and they are very susceptible to not using it for aerospace. So we want to break that barrier. We went to the fundamentals and looked at what we call the crack stress intensity at the crack tip, using this expression with the wet function, applied stress, and the characteristic length. In our case, the applied stress was same, and if we look at a surface flaw, which would be 0.65, so these were same. We looked at the LC value for this build orientation, and we measured that LC from the fracture surface, the critical length, characteristic length, and we found for all three build directions, the critical stress is about 29 megapascal. And that explains why we didn't see the effect of 0, 45, and 90-degree build. That's the understanding we found through fractography analysis. Then we looked at, if we do a post-processing, which is a second step to improve fatigue life, what will you see? So you could see the black dots are as-built data, and the machined and polished data are red dot. Again, for low amplitude loading, we see higher scatter. And for high amplitude loading, we clearly see machined and polished are grouped together, and they improve the fatigue life. You can see clearly the roughness changes. Machined polished surfaces have a roughness 300 to 1500 nanometer, but as-built can have 2500. So you can see clearly different stress loading, as-built has much lower life, at least 1/3 of the machined and polished cases. And for the lower stress loading, of course, the same thing persists. So we found basically it's clear if you improve surface roughness, reduce surface roughness using machining and polishing, it pays off. You get definitely much higher fatigue life. You eliminate all the fatigue issues coupled with surface roughness. But in our case, porosity was very small, so there was no effect of porosity. But if you have large pores or multiple pores, even if you remove the surface roughness effect, you may not get the right answer. You may still get a lower fatigue life. So coupling of different defects is very important. Then we look at what is going on in terms of different pores. As I said, we normally get gas pores, which are spherical, lack of fusion pores, which are kind of irregular shape. And the average height of these satellites is about, we found 25 micron, which is an issue here because 25 micron is kind of the initial crack length we find in aerospace metals, which is similar to the height of this satellite, which is unmelted particles within these AM structures. So poor surface quality of as-built samples is causing early failure, but this surface quality is affected by these defects, which are lying in the proximity of the surface. And they are even making the thing worse by causing fatigue crack to initiate from the surface from one of or multiple of these different types of defects. Then we looked at the limitations of as-built samples. Fundamentally, you can see here multiple crack initiation happens, which causes fatigue failure for as-built samples. Whereas machine sample, we have a single crack. And you can see for the same stress amplitude, this is a single crack, which causes fatigue failure, there's a multiple crack. And that's what we can see. The machine surface has a almost 3 times fatigue life. If we look at as-built sample at a lower stress amplitude, even in that case, you get a higher fatigue life, but still we are dealing with multi-site failures, which could be an issue. So multiple crack initiation site in the as-built sample produces poor surface quality, and that is causing fatigue life loss. Even at a higher load, machine surface, normally we found they are controlled by a single crack, single or maybe 1 or 2 cracks, but not multiple cracks certainly. So this is a summary of effect of post-processing. Sorry. Now we looked at the porosity fraction. Higher percentage of near surface pores we are observing in as-built samples. And if you have a machine surface, we can see the porosity fraction goes down. If you look at this closely at the surface, as-built sample has much larger fraction of porosities, 2.5, as opposed to machine surface, where the porosity is only 1%. So this shows by reducing the porosity, you are actually improving the surface quality and the fatigue performance of this AM component, so which is a critical factor in our AM-based material design. So let's move on. So this is the summary, what we have learned from our experiment, and of course, analysis of data about how the post-processing parameters affect as-built and machine sample. Machine sample shows about 80% increase in fatigue life, and for the lower stress loading, it can be a double, 90% increase, but there is an increased scatter at the lower stress loading, which you have to take into account in your design. Finally, the surface quality is the key factor, which causes early failure. Multi-site crack initiation in as-built samples is a serious problem which we need to address. And the porosity, the large numbers and fraction of pores in the near surface also causes the failure. So this is a summary what we found. Then we looked at surface effect, more detailed, machined versus machined and polished, and we can see these are vertically machined samples. What we found, the change in surface roughness value, there is no easy shortcut linear way to scale or apply similitude to predict the performance. You can see it's scattered all over the place. At a higher loading, you can observe some close values, not so much scattered, but at a lower loading, such as black dots, the scatter in although the roughness values are very much scattered from 500 to 1,000, but the fatigue performance are nearly the same. Okay, so it doesn't scale linearly with the roughness. Then this is a summary which summarizes the data from machined and polished for these 4 trace amplitudes. With the as-built, you can see the as-built have a clearly low fatigue life. There is no simple relationship. Significant variability was observed in surface roughness and corresponding fatigue life. But with the machined and polished samples, with the similar roughness values, which is to say solid black squares, the fatigue life can be at least 70% variable. Even the samples we tested as maximum stress, which is the red dots here, have a similar fatigue life, although there is a significant variation of roughness. It can be 2 ways. Significant roughness variation can produce similar fatigue life or quite different fatigue life for very close roughness. So we can have a not really good correlation, as you see with the diagram. Very small variation of porosity fraction and pore size. The variation of fatigue life, this is a key message, doesn't correlate closely with the pore fraction or overall volume of porosity. The pore size we found to have a greater effect on fatigue life than porosity fraction, particularly at lower stress loading. So why all this happening? What is the problem? What we are missing here? What's the missing link? This is the missing link. Fatigue is controlled by what we call notorious pores, a local effect. Look at these 2 data. Same roughness roughly, same porosity fraction, same stress amplitude, but on the right-hand side, we have a fatigue life which is double that of the left-hand side, 143,000 as opposed to 300,000. What makes difference is the defect which causes fatigue failure, particularly if you have a single site failure. This area, the effective area is 4,500 micrometer square, 308,000, and that is so highly sensitive and makes a difference in fatigue life. So this explains a lot of scatter, a lot of lack of correlation we observe between surface roughness and fatigue life. Let's look at summarize what we found, what lesson we learned in this diagram. We considered the porosity effect at low stress level because higher scatter is found in this region. That was our problem. We couldn't relate with porosity very well. And what we find here, look at this diagram, vertically built and horizontally built. For the same stress amplitude, if the pore size is smaller, you get a higher fatigue life. Very good news. Same stress amplitude, pore size is smaller, as dotted by the circle, you get a higher fatigue life. However, look at that solid and hollow pores. If the pore is close to the surface, same pore size, subsurface internal pore is less critical than a surface pore. If the pore of same size is on the surface, it will be giving you lower fatigue life. If the pore is internal, although the stress level is the same, you get a much higher fatigue life, and that happens both horizontally built and vertically built cases. So this is a good take-home message for us. Whether the pore is on the surface or internal, and if it is internal, then the size will dominate. If it is in the surface, then the size effect will dominate. Then look at this one. We are almost closing. One point we often ignore in fatigue performance, particularly for additive manufactured cases, are the shape effect, which we found to be critically important, which is often not considered. Look at these two cases. On the first row, we have gas pores compared with lack of fusion pore at a low stress level, 120. A lack of fusion pore, which was the critical defect, produced a fatigue life of 100,000, whether the gas pores produced 5 times more. Same happened with the lower stress level, lack of fusion pore, and the gas pore. With the gas pore, fatigue life is at least 4 times. Why is it? We know from lack of fusion pore are notoriously tortuous, arbitrary shaped, and it has got a lot of local stress concentrators embedded within a pore, which becomes highly fatigue critical and can raise to a crack and propagate the crack and initiate and propagate the crack at a much lower load. And it can significantly lower the fatigue resistance as we found here. So very tortuous lack of fusion pore are more critical compared to gas pore, and that is the key effect why we find at lower stress amplitude a high scatter with porosity because of the shape of the individual critical pores, which is causing the fatigue failure. Finally, I'll finish up with the last item we talked about is the stress loading ratio. We looked at tension loading and tension compression loading. This is very familiar curve for us. The fatigue life will decrease in a log linear fashion. But the important thing is tension loaded samples has a reduced fatigue life and higher scatter compared to a compression tension sample. Why is it? We all know the crack closure effect. And in this case, we talk about a pore closure effect. So if you have a compression sample, R -1, you can see compared to this CT diagram, many of the pores are closed and not visible below threshold. Whereas if you have a tension loading, you see a reverse effect. The pores are opening and you get more pores. This is kind of summarized, pore frequency with a ferrite diameter. As you can see, before the test and after the test, the porosities are reduced. The critical pores, the lower diameter pores, are more reduced. You can see the blue one is the initial and the red one is after compression, after you load it. It's reduced, the lower pore is reduced, whereas it's opposite. If you have a tension loading, the blue and the red line, the pores increase in diameter. And that is clearly demonstrated. Increasing count of tiny pores in tension fatigue test compared to before the test is causing this lack of the lower fatigue life for tension loading. This is another effect we can see going too deep into fracture mechanics, and this is the last, I think, 1 or 2 slides. You can see for a completely reverse loading, tension compression, fracture surface, this is tension. Look at the stable crack growth region and unstable crack growth region from the micrography. We can see crack nucleates at subsurface pores for both the stress loading conditions, which is okay. Stable crack propagation zone in B is higher than the unstable crack propagation zone C in the case of compression tension loading. And this is due to the crack closure effect that increases the plasticity. And this demonstration between the stable and unstable crack growth zone between tension, and compression causes the lower fatigue life for tension loading as well, which we need to take into account for AM. Finally, heat treatment. We studied heat treatment effect also. It's relatively simple. As-built machine heat treated, you get no failure. Generally, it's a universal finding, post-processing and heat treatment. Peak hardening, machining, along with heat treatment will definitely affect and will improve your fatigue life, which is a clear outcome. And in this case, we can see the clear relationship. And this is again due to the grain boundary. No heat treatment has got a fine grains. If you have a heat treatment, in this case, we find it exposes a lot of silicon particles. So grain boundaries promote the growth rate once the crack initiates at the surface and subsurface pores. Once the crack initiates from the surface, finer grain boundaries which promote the growth, while if we remove it, this hardened silica particle will cause crack growth. It will slow down and resist the crack growth. So this is what the heat treatment causing the difference. With that, we have proposed finally what we call, this is obviously a more fracture mechanics study, which I would omit due to the formation of what we can see. If you have a non-heat treatment, the dimples have a cleavage facet and dense shear ridge, which promotes quasi-brittle fracture. But if you have a heat treatment, we can see more of a dimples, round dimples, which promotes more ductile fracture. And that's another mechanism by which heat treatment improves your fatigue life. Finally, we come up with a modified version of the Murakami equation by changing the factor Y to what we call gamma. This is quite important. We proposed it because we can find a modified stress intensity factor which can better kind of capture our fatigue strength or NK distribution, NK graph. We use the CT data and local maximum stress, KT times sigma, which we can use in this formula, and it can also accommodate a large pore diameter, and it uses a ratio, which is the pore diameter to distance from the surface, and which leads to higher stress concentration. So basically, the ratio between the local stress to applied stress around the pore, it leads to a lower fatigue life. So this formula, although it's empirical, it's very crude. It tries to incorporate some of the phenomena we observed, which is the size of the pore, proximity of the pore to the surface, and how we can take into account with a modified factor K mod in our equation. So that's the summary. What we found in our work, particularly for the aluminum alloy, as-built samples, the average surface roughness values acts as the key factor. If we use machine polished surface quality and subsurface porosity would be the reason, and that we should pay attention to. The effect of porosity is controlled by location, size, and density. This order, so the pore locations are critical, and we need to remove pores on the surface. That will significantly degrade the fatigue life. Finally, if we have lack of fusion pores more, that could be critical for us because they are much more critical than the gas pores, which is spherical. So lack of fusion pore could be a notorious defects, which can significantly degrade fatigue life. Heat treatment is a great way to improve higher fatigue life and lower crack growth rate due to improved ductility, but the crack closure effect, the fracture surface for the compression tension loading will show more fracture and we'll have a higher fatigue life. So that summarizes the finding. This is some of the references, and thank you very much to all my colleagues and also all my students and research funding. And last but not the least, my thanks to all of you for attending the presentation, ECF committee, and particularly Chair Professor Jelko Bojic for inviting me. Thank you very much.